Any questions before I start?
I was going to see if you could go back over what you were doing at the end of the last class, like finding using the Fourier to...
It's the Laplace or Fourier transform. This is section 7, right?
Right.
All right, how about we just
Find
do
like the
3,
moments or something?
how about we do 3-7.1? And we'll just sequentially go through them, all right? Ready? How about 3 points?
Can we do the exercises too?
Yeah, which one would you like?
The second one.
What, what page is it on?
The second.
Is it exercise 3 tac 7.2?
Exercise 3-7.2. This is exercise on page. Just give me the page, please.
152.
152. Okay, let's do it. Go ahead. Give me the specifics. He'll give it to me.
Okay, random variable x has a probability density function of the form f of x equals 2e to the negative 2x u of x. And then using the characteristic function, find the first and second moments of this random
All
variable.
right, pay attention. Pay attention. Everybody? All right, first and second moments. How would you normally do it? This is the expected value of x, right? Normally, what do? We take the integral of x times f of x from minus infinity to infinity dx. That would be the first moment, right? Second would be this squared. Do you all follow me on this, class? All right, let me do it this way. All right, now, if you use Fourier or Laplace transforms, I'm going to use Laplace for this one, all right? Now, I'm going to make one comment. If f of x had values from minus infinity to plus infinity, then I'd go with Fourier, because Fourier is defined over that domain, all right? This is defined over 0 to infinity for x, all right? So I'm going to use Laplace. When I use Laplace, I know that f of s, all right, is actually equal to the integral of, and you can put, this is a dummy variable, I'm going to put it in here. It could be t, it could be y, it could be x, it doesn't matter. F of x e to the minus sx dx from 0 to infinity. Do you all follow me? Now that is the definition of Laplace, but instead of t, you're used to seeing it taking a function of time to a function of, really to s, which is a complex plane. It doesn't matter if it's t or anything else. The Laplace transform is not going to be a function of the other variable. It's important you appreciate this. So when I take a look at this, then I take a derivative of f of s with respect to s. Then I get this. I get an integral, still integral from 0 to infinity. It's still going to be f of x, but I take a derivative with respect to x. It comes out at with respect to s, minus x times dx, right? Can everybody follow me? That's the definition of Laplace transform. A derivative of Laplace transform. Now I make, yeah.
Wait, why wouldn't the e there?
Yeah, it is there. It is. It's going to go away in 1 second. Sorry. E to the minus sx dx. Sorry. You're absolutely right. For completeness, let me just do this. I'm sorry. I don't mean to rush through this. All right. Now, does everybody follow me? Now, what happens when you take s and let it be 0? That goes away, right? What is that? Well, it's actually minus the expected value, right? So if I multiply this by a minus, then that is the expected value of x. Do you all agree? You asked this, right? Or who asked this? You did. Y'all follow me? All right, now let's do it for this problem. First, I have this. So I have f of x equal to 2e to the minus 2x u of x, right? The Laplace transform of that, I'm not even going to bother with this, is just 2 over 2 plus s. Do you all agree? This is one of these kind of no-brainers, but I'll put it up there for you. All right, you all with me? All right, now, take a derivative. Do you all follow me how I got that? That's f of s. Take a derivative. This is my f of s. By the way, you can do it. You can do it this way and still get. You can do it by the formal definition and still get the right answer. But it's integration by parts. It's a little more irritating, in my opinion. Come over here. Take a derivative. If I take a derivative of f of s with respect to s, then I let s become 0, and I put a minus sign. I get the expected value of x, because the the functional form here is x. So now I take 2, right? And it's going to be minus this. And it's going to be s plus 2 squared times the derivative of that. Do you all agree? I mean, how many agree with me there?
How did you get the squared?
And I got to take a minus. Well, I have 2 plus s to the minus 1, right? Derivative of that is what? Minus 1 over 2 plus s squared, right? Times the derivative of s is just 1. But there's got to be another minus sign here, makes that plus. Now I evaluate that at s equals 0, and it is what? 2 over 2 squared, or 1/2. Do you all agree?
Is that just the formula? Is there a negative for Laplace?
No. What I'm saying is this, if I take a derivative right here, this would have a negative, right? Now I need to multiply it by negative so I get a positive, and that is the definition of the moment. Do you all follow me on that, class? You good with this?
The other one, where it's J, where you multiply.
No, that's Fourier. We could do it with Fourier, all right? But, it's going to come out the same. Laplace is easier because you don't have to fuss with the J.
So the J is basically just changing the sign to a positive.
You mean when I multiply by J, if it's a Fourier, yes. It's going to be a positive value. You can kind of tell this function only has values that are positive x. You can't have a negative mean if it only has positive values for x. Okay? You all with me? Did that? I'm going to. Did you? Hold on for a second. What? Did you have another part of this or not? Is there another part?
The second part is fine, the second moment.
All right. How do you get the second moment? Fake. Yeah. Hold on. All right. So this is the first moment, but I'm going to go back to this. Let me go here. All right. So this is the transform, right? And I'll put the minus sign. This would be the first moment, right? Sorry. Let me actually do this. I'm going to put in e to the minus sx dx here, right? That's the first moment, and I'm going to, it would be after I multiply negative, but I have that, right? What happens when I take a second derivative with respect to s? Just take a look. With respect to s, only in here, right? It brings out another minus x. Do you all see that? Now I get a second derivative of this right here is going to make that positive x squared. Do you all follow me? Now, if you let s go to 0, what is that? That is the second moment, right? That's the expected value of x squared. Do you all agree with this? It's not hard. And if you did your homework, this should just like, oh yeah, this is trivial compared to some of the, like integration by parts twice for an x squared e to the minus ax kind of deal. All right, so take one derivative, we get what? Minus 2 over 2 plus s squared. That's one derivative, right? Take another derivative, what do we get? We got minus 2 over, now there's a minus 2 here, comes out in front, minus 2, right? Then it becomes s plus 2 cubed, right? Derivative of s, the inner part with respect to s is 1. Now you get a plus here because they're both. Now you evaluate this at s equals 0, and this is the expected value of x squared. And what is that? That's 4 over, isn't that 4 over 8 or 1/2 class? Do you all agree with that? Is that the answers they have? I don't know. I think it is. Okay, that's, what exercise was that? First or second?
This was the second exercise.
How do you, the first one did everybody have down? First one is what? You take what? A couple of, what is it asking for?
It says for two random variables in exercise before.
We did that one, right?
It says, yeah, I think we're.
We just take the Fourier trans or the Laplace, let's do Laplace of both, right? Then you go ahead and say, well, convolution in one domain is multiplication in the other. You multiply them together, then you do partial fraction expansion, find the coefficients and go back to the z domain, right? Or the z domain, right? And then you got it. Remember that? And it was a double exponential, if I don't miss my guess, right? All right, I want to move through. Let's do the x. I don't think we did 3-7.1, did we?
The exercise?
No,
Or
the problem.
We did the problem last class.
We did one?
Right at the end.
That's doing the applause and then doing the partial fraction.
Yeah. But that's what this is going to, it's either Fourier or Laplace, and it's basically skipping the formal convolution. 7.2, problem 7. Let me erase this. I don't mean to be in such a hurry, but I want to cover some stuff today. I mean, these are not hard. These are basically the easiest problems you can get right here, but it's going to get complicated. Well, I say it's going to get, you know how section 3.5 was more, it was trickier because it had that, like the cosine with a random buried in that. You had those trig identities, and you had to define f of z's range based on the functional form that they gave you. In this case, a cosine. It's a little more pain in the butt, but most of these are going to be easy relative to that. Go ahead. 3-7.2.
Yep. Find the characteristic function of a Gaussian random variable with zero mean.
This isn't hard. All right, it is hard if you haven't done it. All right, no, it's not. So what is a Gaussian? So give me the Gaussian f of x is what? 1 over square root of 2 pi sigma, right? And then it's exp to the minus, is the mean a 0?
Yes.
All right, so it's really just x squared over 2 sigma squared. And this is over the extent of x values, from minus infinity to plus infinity, right? Now, they want the transform. This has to be a Fourier, because this is defined from minus infinity to infinity. And I want to underscore this one fact. If you have f of s, this is a single-sided Laplace transform you were taught and almost everybody uses. It goes from 0 to infinity of f of whatever. It doesn't matter if it's t or what, e to the minus st dt. You'll notice the lower limit is 0. That means if f of t has values, for negative values of t, this won't work because it doesn't have a range to go there. You all with me on this? There is something called a two-sided Laplace transform. You aren't taught that and you don't know about it. It's more, the tables are more involved. But if you look at the Fourier transform, right, that's equal to the integral from minus infinity to infinity of f of t, and it doesn't matter what that variable is. T, z, doesn't matter. F of t, e to the minus j omega t dt. Now this does start at minus infinity, right? So it will capture any negative possibilities for f of x, for x being negative. You all with me on this? So for this one,
Is it positive j omega t?
that's in the book. That's their characteristic function. I'm going to do, what do they want, the second part of that one? I'm going to, it's a Gaussian, right? We're going to get the characteristic function, but we're going to get my characteristic function, which just has a positive, it has a negative j omega. Theirs characteristic function, for some silly reason, has a positive j omega, right? It's fundamentally the same thing. The signage will change, but let me just do this. So if this is, all right, f of x, right? Now just follow me on this. All right? If you look at this, what else does he state in this one? I forgot exactly.
He said the variance is sigma squared. And then for part B, I mean, that's all it says. It just says find the characteristic function.
All right, we'll do it. So I think let me be sure I get this. So if we take a look at this,
we can lift out the 2 pi square root sigma.
the what? 1
1
over 2 pi, square root of 2 pi sigma, e to the minus x squared over 2 sigma squared. Isn't that it?
Yeah, I think sigma is like constant for the integration.
Yeah, they multiply the exponentials together and then put them.
No, just wait. This is easier than that. All right, hold it. If I take a derivative of this, let me make this t. This will make more sense to you if I do it with t, I think. Let me try this, t squared. You're going to see this in a second, I think. All right, so I'm going to make it t just because you're used to seeing f of t goes to f of j omega, cap. All right, so if I take this and I take a derivative, by the way, I looked this up. I was trying to brute force it. That was a stupid thing. With respect to t, right here, then I end up getting what? Well, I get minus t over sigma squared right here. And then I get f of t here. Do y'all follow me? Now, if you look at this, once I take a derivative of this, I have to take, it becomes e to the minus t squared over 2 sigma squared, divide this front part, 1 over square root of 2 pi sigma is going to remain. And I have to take a derivative of this with respect to t, which brings out 2t, right? I mean, it brings out 2t over 2 sigma squared. The 2's cancel, you get this. Do y'all follow me? All right, now take a Fourier transform of both of these things. Well, this becomes what? J, I don't know if he does it this way, by the way, times f of omega, right? Do you remember that? Right? What about this? Well, this is equal to minus 1 over sigma squared. And if we know that f of t goes to f of omega, which is equal, you don't have to write this part down, of f of t e to the minus j omega t dt, then if I look at this and I take a derivative of this, f of omega, with respect to omega, I end up getting, it becomes a minus j here, and then you get t, f of t, e to the minus j omega t dt from minus infinity to infinity. Just follow me on this one. You all with me? So you can take a look at this, that if I have t times f of t times f of t here, and I do a transform, I'll put this way, minus 1 over sigma squared, and now we have t f of t, and I want to take a Fourier transform of both sides of this. Y'all with me, class? Well, what happens? If I multiply both sides by j, I get this, don't I? So that is, if I take j times df of omega d omega, that is the Fourier transform at t times f of t. I come over here and I do it, and now I have j times f of omega here, right here. Just bear with me on this one, okay? Now, next thing I'm going to do, well, I can take 1 over j, I get minus j, so I put j down here. And now I have this, right? Y'all agree with that? And then, what happens at the end of the day? That this is going to be f of omega here, and I'll leave it by j times sigma squared is equal to, oh, hold it. Let me do it this way. I'm going to do it this way. I'm going to leave the minus 1 over sigma squared, and I'm going to put, plus j down here. And then that's df of omega d omega. Now, the only thing I'm doing is I'm going to put the j here, so it becomes 1 over j here. And then you can take a look at this. This is a differential equation. Do you all follow me on this, class? I'm not going to ask you something this complicated. All right, but I'm going to tell you the way you can do this problem. This is one method. You can brute force it. It's a pain in the butt to go ahead and do the integration, the formal integration of f of omega. When you put that Gaussian, you can do it, but there's many steps to that. If you do it this way, what happens next? And I'll do it over here. How many are with me at least what my idea is? I'm going to circumvent that by doing the solution to the differential equation. Then over here, what happens? Let's see. Now I have, let me do it right here. So I'm going to have df of omega on that side. I'm going to divide it by f of omega equal to, and then on that side I have j omega times j, which is j squared. The minus sign then goes away, so I'm going to have omega times sigma squared, and it's going to be d omega. It's just a differential equation. I'm trying to get rid of those j's and stuff to make it a simple one, right? Now, if you integrate both sides, this is one of the few niceties of doing it this way. If you integrate both sides from 0 to omega, you're going to get, this is the natural log of f of omega. Does he do it this way, by the way? I don't. Okay, this is a classic way of doing it. It's in engineering and in math, you try to find the simplest way to solve the problem without making any judgmental errors or assumptions that aren't valid. You all with me? Over here, I get natural log of f minus natural log, well, I just call it natural log of f minus natural log of f of 0, that would be f of omega 0, is equal to, and this becomes sigma squared omega squared over 2. And therefore, this one will be 0 because this is a Gaussian distribution for the statistical thing, and it's got a mean of 0. So that part will go to 0. The f of, remember, the only time you have a 0 value is if you have a DC component. Do you remember? If you have like 1, it goes to a delta of 2 pi times delta of omega in the frequency domain. If the average value is 0 of the function, then the transform of that goes to 0 in the frequency. You all with me? So just move on with that. That goes away. Now I have log of the function f of omega equals that. If you get a log, and there's a minus sign I dropped somewhere, I think maybe here. But next, when you go ahead and do this, I just take everything e to everything, all right? E to the log of that just as f of omega. I hope he has this. And that's going to be equal to exp to the minus omega squared sigma squared over 2. Is that what he has?
That's the right answer.
Yeah, that's what he
All right, that's the way you circumvent doing that crazy integration that I had up there a second ago. He must do it. I looked at that thing, I started messing with him there. Got to be a better way. And I just looked online, and they said, you know, do the differential equation. So I'm just leveling with you. I didn't remember that off the top of my head. I had to look it up. Does that make sense to everybody? Next part, what is it?
He takes us back to section 2.5. He said
Wait, in this problem?
in this problem. Yeah, because he's asking to use this characteristic function and then verify the result in section.
Okay, all right. So first and second moments, that's a Gaussian we took the transform of, right? Hear me on this one, this is important. So we have now the transform of the Gaussian in the frequency domain, right? It's Fourier, right? Here's your thing about Fourier. So when we take a look at this, and now we want to know what the moments are, he has first and second moments. Just think about it. If we have Fourier transform, and let me go here. Did anybody try to do the integration on this one, by the way?
Yeah, I think
It's a pain. It's really a pain. I was going down that path for a second. I try to do these things without ever looking at the solutions. I'm going, there's got to be a better way. I mean, this is just insane to do it. But, you know. Anyway, so now the next thing I'm going to do is this. Think about the definition of a f of omega. And I don't mean to bore you with this. Most of you know this by heart, or at least I think you do. Integral from minus infinity to infinity of f of t e to the minus j omega t dt. Now this should be at some point in your careers about as common, as well known as v equals IR. I'm telling you, you'll use this as seniors, any seniors in here? When you get into senior classes, I mean communications, think about all these things, all the wireless stuff, everything. Fourier, Laplace transforms all the time. Anyway, come down to that. Now we take a derivative with respect to omega, right? And what do you get? Well, I still have that integration from minus infinity to infinity. The f of t now appears, right? But when I take a derivative of this with respect to omega, it brings out a minus j and then t, right? I'm going to put t here. And then times e to the minus j omega t dt, right? Now it's starting to look familiar. Now, if we multiply through by j again, right? J times j is minus 1 with a 1. It's plus 1, we get that. Right? So when we take this Fourier transform, multiply it by a j, we get this. And then when you evaluate it at omega equals 0, that goes away, right? Can you all see this? If that goes away, what is this by definition? It's the expected value of that function t, or x. If you wanted to use x, it would be x f of x df of x. That's the expected value of x. Do you all agree? So that's my point. So now we have f of omega. To get the first moment, we take a derivative of that with respect to omega and evaluate it at omega equals after multiplying by j. It won't matter in this one. Take one look at this. If I take a derivative of f of omega, what do I get? Well, I'm going to get e to the minus quantity omega squared times sigma squared over 2, but then I have to take a derivative of this, and now I'm going to get minus 2, right? Omega sigma squared over 2, right? Don't worry about the rest, but I have to evaluate this at omega equals 0, regardless if there's a j there or not. What happens? It goes to 0, doesn't it? Because there's omega in front. You all see that? Everybody? Doesn't go to 1, the exponential does, but the omega equals 0 makes it 0, right? That's the first moment, right? And if you wanted to, let me just leave it. That's it without the j, but 0 times j is still 0, right? What's the second moment? That's the first moment, right? And second moment is what? Take another derivative of this. Let me see if I can just make this uncomplicated. Right there, right? So I can take the sigma out in front when I do this. How many see this by now? F of omega. Second derivative with respect to omega. All right, I'm going to take the sigma out minus sigma squared out in front. What happens when I take another derivative of that? Right here, I get what? Derivative of omega is 1, right? So then I get the exponential e to the minus omega squared sigma squared over 2, right? And then it's going to be plus omega times the derivative of this, which is going to be what? Minus, think about it. I'm going to get, with respect to omega, the derivative of this is going to be minus 2 omega sigma squared over 2, or minus omega sigma squared here, right? And that's going to be times the exponential. Again, you're going to see that exponential has no bearing on this right here. And you got to evaluate that at what?
Omega 0.
Omega equals 0. And actually, now there is another j, so that would become positive. So when you get j squared times this, they'll make that positive, and I evaluate that at omega equals 0. What happens?
It goes to what?
Or sigma squared.
Yeah, sigma squared.
Yeah, sigma squared. Because the w would be 0, so that all goes 0, and then e to the negative 0 is 1, so you're just left with sigma squared.
Is that the right answer? All right, y'all follow me on this? So your friend are these transforms, but if, again, if the extent of the f of x or f of y or whatever, f of z has minus values, in other words, non-zero minus values, then use Fourier. If it has, if it doesn't have any values for less than 0, right, for any of the variables, then use Laplace. It's easier, in my opinion. You good with that? Let's do the next one. Is there another part to that? No?
No.
I think the next one's the Bernoulli thing.
Yeah,
Is that right?
yeah, Bernoulli distribution.
Bernoulli, he gives you the characteristic function, right? In there, he wants first and second moments, right?
He was the mean value.
That's first moment.
And then mean
Mean-
square value.
Yeah, mean squared value, so the only thing, that's the second moment, right? So it's just derivatives of his characteristic function with respect to, in his book, u, because he doesn't use mine, right? I prefer using, I like the definition of the Fourier because you're familiar with it. You're not familiar with characteristic function. The only difference is when you go into the omega domain, this omega right here, it's going to be minus the actual argument of omega. You're going to see if it's an even function, it doesn't matter. And I don't want to get hung up with that. Stick with Fourier, okay? Now, next part.
And he also wants the third central moment of that random variable.
Again, a third derivative.
Okay.
All right, and so I'm not going to bother with the Bernoulli one because, frankly, he uses his characteristic function there, but it's the same method. It's just first and second derivatives, and then third derivative, which is longer. I was working these problems, and I'll say one thing though. He does select problems that cause you to be careful with your derivatives and stuff. So you have to have a fairly good focus to do these things right. All right.
All right. The next one looks like a good problem.
Which is it?
3-7.4, two statistically independent random variables, x and y, have probability density functions given by f of x equals 5, e to the negative 5x.
5? Okay.
Yeah.
5.
E to the negative 5x, u of x, and then fy of y equals 2 e to the negative 2y, u of y.
All right, what does he want?
First, for the random variable z equals x plus y, find the probability density function of z using the characteristic functions of x and y.
We're not going to do characteristics. Are there any negative values for f of x or f of y that are non-zero? What are we going to use?
Laplace.
All right, Laplace transform. So in other words, we're going to say instead of taking f of z equals the convolution of f of x, or I should say f of z convolved with fy of z, we're going to go right to the transform domain. We're not going to bother with convolution. It's the whole beauty of transforms. You omit a lot of the tedious mathematics. So for the transform, we know f of, I'll put it this way, f of z here will be equal to, take the transform, this is in the transform domain over here. All right, so it will be equal to, give me 1 second, you're right, but just hang on for 1 second. So it's going to be equal to, when I transform it, I get 5 over 5 plus s times, and then it's going to be, what is it, 2 over s plus 2. You all agree with this? I'm just doing it for completeness. Now, these are single poles. We're going to break it down to 2 poles, right? You all agree with this? So this is going to be some a over s plus 5 plus b over s plus 2. Almost always, and I can't think of an exception right now. Whatever you find for this one, this is the minus that. Because these are 2 simple poles, and the top part doesn't have s in them. Y'all with me? If it had s in it, they'll be different. So what do you find out for a? What is it? Cover up, right? Cover this, right, and let s equals minus 5. So I have 10 over minus 3 or minus 10 thirds. Take a good look. Make sure you agree with this. What's the next one? Over s plus 2, correct? This is basically what I did in class last time, I think. It's almost exact. Okay, what's next? Take it to the what domain? I was in the transform S domain. I'm bringing it back to whatever this domain is z, isn't it, class? Right? Because it's f of z. So what is f of z going to be, guys? Inverse. Well, what is this going to be? You know it's 10 thirds in front, right? So I can say it's 10 thirds for both of them. This has got a minus sign, right? And what's the inverse transform? And I'll leave this up here for the quiz. If I have e to the minus at u of t, remember it doesn't matter if it's xt or whatever, the the Laplace transform of that is going to be simply 1 over a plus s. Might as well put the Fourier transform of that up. That's Laplace. If it's Fourier, e to the minus at u of t goes to 1 over a plus j omega, correct? All right, just put that up here. So this one goes to what? E to the minus 5z, and it's going to be plus e to the minus 2z u of z. Do you all follow me? Is that the right answer, by the way?
Yes, you could.
All right, what's the next part? How many see this, by the way? Everybody? Okay, go ahead.
The next part is to find the first and second moments of z.
Okay, guys. Now, there's 2 ways. There's the brutal way where I multiply this by z, right? And then integrate it over where z exists, correct, class? From 0. That would be, that'd be a pain. I mean, you can do it, all right? And I guess with your calculators, maybe it's not that bad.
How would you put a step function?
Oh, you're asking me the wrong thing. I don't know. Step functions probably have Heaviside in the calculator or something like that. What is it?
You'd have to install your support function.
Yeah, TI can do Laplace.
Oh, can? It can do Laplace?
It can without like install additional. So
Install away. All right. How are you going to get the first and second moment?
Derivatives.
Take the derivative of that, right? And then do what? By a minus sign for first moment, and then set s equal to, all right, want to do one? We'll do the first one. All right, so for the expected value of z, now I've got to take derivative of this, all right? So derivative of this I'm going to put 10 thirds out in front. So then I got minus 1 over 5 plus s squared. That becomes 1 over what? 5 plus s squared. Do y'all follow me? I took 10/3 out in front. There was a minus sign, but when I take the derivative of 1 over 5 plus s, I get a minus sign out, so it kills the minus sign there. Do y'all agree with this, class? Next part of that is what?
Minus 1 over s plus 2 squared.
Right? Now, that is the derivative of this, but to get the expected value, I have to multiply it by a minus, don't I? You all follow me on this? Because of the definition of f of s, right? I'm sorry if I'm going too fast.
Why we multiply one?
All right, well, think about the definition of f of s. And I'll put this here, too, for your quiz. F of s.
I'll take it. The game did.
F of s, I mean, you guys should know this, but f of s is equal to what? The integral from 0 to infinity of f of anything. I can use f of t here, e to the minus st dt. So if I take a derivative of f of s with respect to s here, I'm going to end up getting a minus the integral of t and f of t e to the minus st dt from 0 to infinity. Do you agree with me? Now, I don't want the negative value at the moment. I want the positive. So I multiply this by a minus sign, and then I evaluate it at s equals 0. And that is the definition of the moment, because e to the minus st goes to 1. Everybody okay with that?
And then when you take the second derivative, the minus is still 1.
The minus will cancel. All right, and it's sort of a no-brainer thing. Just listen. F of x and f of y have non-zero values only for positive values of x and y, right? Z can only have values that are non-zero for z greater than 0. The moments have to be on positive z. They can't be negative, just as a brain check. Y'all with me? Okay, so that's what is this going to be? So this is going to be, I can multiply through, and I'm going to get 10 over 3, and then I have to say s equals 0. So that's 1 over 2 squared. Tell me if this is right. Minus 1 over 5 squared. So that's 10/3 times, what is that? 1, it's squared, is it? 1 over 4 minus 1 over 25. What is that? What is that? So if it's 100, so it's 25, so it's 21 divided by 3 is 7/10. Is that, what?
That is correct, I'm pretty sure.
0.7.
Okay, let's see. Yeah, that's right, 0.7, because the denominator would be 100. That's right. Okay, is that the right answer? How do we get the second moment? Now you can take another derivative of this, right, with respect to s, set s equal to 0, evaluate it. If by chance it's negative, because you were running through this too fast, like I typically do, just multiply it by a negative. You all with me? It's going to be a weird number, though, I think, because when you get a second derivative of this, another derivative, now you get what? Minus 2 coming out here, right? And you got 5 plus s cubed, and then on the next side, you're going to get a minus 2 coming out, and you get s plus 2 cubed. And maybe it isn't that bad. What is that? 1 over 5 cubed is 125, and then 1 over 8. So you got a 125 and a 1 over 8 that you're going to subtract from each other. Then you multiply that product by 10/3, and that should give it to you. I think, yeah.
I just want to get this clear. So if it's Fourier.
Fourier.
Fourier, yeah, sorry.
I'll put it up here for you. That way.
You would, same process for finding the first second moment. You would make sure it's positive.
But you got to do a j.
Multiply it by j, and then let omega equal 0. Is that right?
Say true.
Either s or omega is going to be 0 when you do the
But
moment.
you got to multiply by j for.
Yeah, in other words, if you just think about it rationally, if you got f of x and f of y, no j's in them, right? Probability density functions. The expected value of z, which is a convolution to, is going to have no j's. It's going to be positive, if it's positive. All right, so, and since you asked, I'll put it down. F of omega is equal to the integral from minus infinity to infinity of f of t e to the minus j omega t dt. Now, I don't use his characteristic function. You're familiar with this definition. In the book, he said it doesn't matter. I don't know why they did the other way. The entire universe uses this. But everybody, I guess, wants to do something to disrupt the normal function of life. Anyway, this is what it amounts to. Is there another part to that one?
No,
The
that was
second
it.
moment I think you can all get, right?
Yeah.
All right, what about the next one?
That was all for 3-Tech 7.4.
All right, let's do 3-7.5, hold on. Because these actually aren't that bad. Go ahead.
Okay, a random variable x has a probability density function of the form f of x equals 2e to the negative 4 times absolute value of x,
This is a little different, go ahead.
and then that's from negative infinity to
Yeah,
infinity.
so this goes from minus infinity greater than x less than infinity. So this is going to be a Fourier. Hint? Okay, go ahead.
And then using the characteristic function, find the first and second moments.
The only deal is find the Fourier transform of this. You can look it up, but we can do it. So the Fourier transform of this, f of omega here, would be technically the integral from minus infinity to infinity. Now you don't need to write this down, just appreciate what I'm showing you. I'm going to put the formal definition out. Now it's 2e to the minus 4x, right, times e to the minus j. I can put a t, no, I'm going to leave it as x, omega x dx right here, and it's got an absolute value. So now what I do is I'm going to break it into a negative integration and a positive integration. In other words, I'm going to say this f of omega here will be equal to the integral from minus infinity to infinity, or to 0, pardon me, to 0 of 2e. And now, if you think about this, I'm going to leave it as minus 4 times magnitude of x times e to the minus j omega x right here, plus, and then it's going to be the integral from 0 to infinity of 2e to the minus 4. Now we're in positive territory, so it's just going to be minus 4 times x times e to the minus j omega x dx. Do you all follow me? I just broke it into two parts. Now the first part, or the second part's a no-brainer, because what is this? That is the Fourier transform of e to the minus j 4x, right? Because it's only for positive values there. With me? How many see this? I know. I don't mean to go fast. You follow me on this one? This is the definition of Fourier transform for f of, or for 2e to the minus 4x u of x, for just positive values. Fourier transform of that is what? 2 over 4 plus j omega, correct? With me? Now over here, what do we have? We can fuss with this. We actually have the Fourier transform for this one right here, a couple of different things. If I make that positive right here, then, because it's going to be, hold it, let me do it this way. Right here, if you look at this right here, I can say that part is the integral from minus infinity to 0 of, put the 2 out in front, and here I have e to the, and now it's going to be, if x is negative, they want an absolute value, that would be negative. It would be e to the 4x, e to the minus, or actually, let me do it this way. I can say it's 2 times e, and now it's going to be 4 minus j omega here, or sorry, 4 minus,
You were doing it right and you just changed the denominator of the last one to negative.
huh?
were
What'd you?
doing-
This, what I want to do is construct this as a positive integration. All right. If I do this and I put 4x here, and I have e to the minus j omega x dx here. When you do the integral, I had 2 twice. When you do the integration, the 2 stays there. But now I have e to the, and it's going to be e to the 4 minus j omega x. And integrating that, you're going to get this. 4 minus j omega, when you evaluate it from, it'll be, now it becomes positive infinity to 0 because of the flip signs there. Or yeah, that would, if you go minus, you can do this. You're going to get this at the end of the day. Trust me on this one, you're going to get that. You all with me on this? You can do the integration. I'm a little pressed for time. So I have this plus this. Okay, now here, you're going to have to find a common denominator. So if I multiply this by this, I'm going to get 16 plus omega squared. Do y'all agree with that? The j terms cancel. Now, here I'm going to have 2 times this, which is 4 minus j omega, plus 2 times the next part there, which is 4 minus j omega. The only thing I've done is got everything under a common denominator. I have to multiply that times 2 and this times that 2. And what does that equal? Put it up here. So let's see. I got 8 and 8 are 16. The j omegas cancel. So I got 16 over omega squared plus 16. And that is f of omega, correct? And they want the first moment of the z. Do you all agree with this, class? Can everybody follow me on this? With me, Sam? All right, so I got to take the first derivative of that and multiply by j, and then evaluate it at omega equals 0. Do you agree?
It's 1 over j.
Huh?
Is it 1 over j?
J. Because it's going to come out with a j times a minus j. Just go with me on this one. Look at this definition right here. Right here. Look, if I take a derivative of that with respect to omega, it's minus j omega t, right? I have to multiply both sides by j, because minus j times j is minus j times j is minus 1, minus minus 1 is plus 1. That's the reason. All right. That said, what is the derivative of this with respect to omega? This would be the first moment. Class, 16 over what? That's omega squared plus 16, what? To the first power, correct? Take a derivative, or to the minus 1. It becomes minus, right? Minus 1. And this is going to be omega squared plus 16 squared. And then I have to take a derivative of that, which is, with respect to omega, 2 omega. Do you agree with this? Everybody? Now we've got to evaluate that at omega equals 0. Take one look.
0.
Is that the right answer? Yeah. Can you all follow me? How do I get the second moment?
Second derivative, omega equals 0.
All right. Now, did I multiply? I didn't even bother with multiplying through by j here, did I? All right, y'all with me? Second derivative, take another derivative of this, right? And you can see because of that omega, when I take a derivative of omega, I get 1, so it's 1 divided by this, plus, and then it's going to be omega times the derivative of that. Now I've got a non-zero value, right? And what is the non-zero? Can you tell me what that answer is? I'm trying to. Has anybody done this problem? I hope you all try to make sure you do all these problems before the final exam, especially in section 5 and section 3-5, 3-7, because these problems are very good in exposing some of the methods and tricks we use to evaluate them. Now, I'm not going to give you something where you got to do an integration like I showed you, a clever way to do that, but I'll give you things that will make sure that you're familiar with the methods. That second derivative of that shouldn't be hard. Setting omega equal to 0 shouldn't be hard. Multiplying by j twice is multiplying by minus 1. Do y'all follow me on that? That's all it amounts to. And then evaluating. And we could do this, but to be frank about it, I don't want to spend the time on it right now. What's the next problem?
That is it for 3-7.
Is it?
That's all.
Now, what is it? I got 20 minutes. I wanted to talk to you about the next section, which is chapter 4. I'm going to go through this. We only have 3 lectures after today, and I know you have a quiz, so I'm just going to talk to you about it. Here's what it comes down to, guys. If we have any kind of a sampling, suppose we know that there are random variables. I'll do it on this board. We got a random variable x, just a random variable. It could represent the number of semiconductor parts created. It could represent the population of the nation, whatever. But I take a sample of that. Then the sample will be a random variable also. Now that's I'm going to put some slides up. This is a random variable that has to do with the entire population. But if I start sampling and I take n samples, then each one of these statistically is a random variable. If I talk about a specific sample Remember, the sample has a certain size, so this is going to have a size of n. N is equal to the size of the sample. And call this N, capital N, is the number of, I guess, the population. Now, if we talk about a specific value, or if you take a look at this, this is a statistical variable. You're going to have to just go with me on this one. If you take a look at the expected value of x of I right here, then you would say it's equal to the sum of all the actual values of I from I equals 1 to n. It's that divided by 1 over n. That should make sense to you. You all with me on this? And actually, in his book, he does this. He calls this, I better be careful about that, the sample size. And this would be the mean of the sample size for one sample. I'm not going to have time to go through this and give you a quiz at the same time. So what I'm going to do is this. I'm going to give you a quiz. So could you fill up this row?